Hello everyone. Today I'm excited to present our NeurIPS paper, Memory Decoder, a pre-trained plug-and-play memory for large language models. This is a joint work from Lumia Lab at Shanghai Jiao Tong University and Shanghai AI Lab. My name is Hao Jiaqi. I'm the first author of this paper. So what exactly is Memory Decoder? It's a plug-and-play memory component that brings domain knowledge to any large language model without requiring any retraining of the base model. The key idea is very simple. We internalize domain knowledge into a small memory decoder module, which can then enhance an entire model family. As you can see in this figure, 1.5 billion parameter memory decoder consistently improves all Qianwen models, ranging from 0.5 billion to 72 billion parameters on the finance domain, reducing perplexity dramatically across all model sizes. Okay, but why do we need this? Domain adaptation for LLMs remains challenging because existing methods force us into difficult trade-offs. Domain adaptive pre-training, or DAPT, requires costly full-parameter training for each model separately and often suffers from catastrophic forgetting of general capabilities. On the other hand, retrieval augmented generation, or RAG, maintains model parameters but introduces significant inference latency due to expensive nearest neighbor searches across large data stores and long contexts. So the question is, can we have the best of both worlds? Can we avoid retraining multiple models like RAG while also avoiding additional inference latency like DAPT? Our core idea is to replace the external retriever with a small parametric model. Instead of searching through massive data stores at inference time, Memory Decoder first learns to imitate the behavior of non-parametric retrievers during a one-time pre-training phase. Once trained, the single memory component can be interpolated with any model in the family, providing RAG-like plug-and-play flexibility with DAPT-like inference latency. The integration is remarkably simple. Memory Decoder works with any base LLM sharing the same tokenizer. During inference, both the memory decoder and the base LLM process the input in parallel, and their output distributions are interpolated using a single parameter alpha. And this approach is very efficient. As this graph shows, memory decoder's inference latency is only 1.28 times the base model, compared to 1.51 times for in-context RAG and 2.17 times for KLM. This was measured on Qianwen 2.5 1.5b augmented with a 0.5 billion memory decoder. So how do we exactly train a memory decoder? Here, we use KR divergence to encode retriever-like knowledge in a compact parametric form. During pre-training, we first build a data store and compute KN distributions for each training example. Memory decoder then learns to align its outputs with these KN distributions through KR divergence loss, while a complementary cross-entropy loss prevents deviation from the underlying corpus distribution. This hybrid objective is our key to success. Okay, now let's look at some results. On Wikitext 103, Memory Decoder consistently outperforms parameter-efficient methods across all GPT-2 model sizes. Most remarkably, and this is the 1 + 1 > 2 moment, augmenting GPT-2 medium with a small memory decoder achieves better performance than directly doing DAPT on GPT-2 medium itself, which has nearly 3 times the parameters. This demonstrates that our approach of learning from retriever distributions captures something fundamentally different and more effective than standard language modeling. A critical advantage of memory decoder is preserving general capabilities. On 9 diverse NLP tasks, including sentimental analysis and textual entailment, memory decoder achieves the highest ever score while maintaining or improving performance across all tasks. In contrast, DAPT suffers catastrophic forgetting, with performance dropping dramatically on several tasks. This validates our plug-and-play architecture. By keeping original model parameter intact while augmenting with domain knowledge, we achieve specialization without sacrificing a generality. The plug-and-play capability really shines in our cross-model experiments. A single memory decoder enhances models across entire families, both Qianwen and Llama, spanning from billions to tens of billions of parameters. Across 3 specialized domains, biomedicine, finance, and law, we see consistent improvements. For smaller models like 2.5 billion, the gains are dramatic. But even for large 70 billion plus models, Memory Decoder provides substantial improvements. Here, we also give a case study. This case study illustrates why Memory Decoder works so well, because it can bridge parametric and non-parametric methods. For long-tail factual knowledge like real names or dates, Memory Decoder assigns dramatically higher probabilities than the base model, successfully capturing the memorization benefits of retrieval methods. But for semantic coherence and reasoning, Memory Decoder maintains probabilities closer to the base model, preserving linguistic fluency that pure retrieval methods sacrifice. It gets the best of both paradigms. To conclude, Memory Decoder introduces a new paradigm for domain adaptation. It is a single pre-trained memory component that can enhance any model sharing the same tokenizer without modifying parameters and with minimal inference overhead. Our comprehensive experiments across multiple domains and model families demonstrate consistent improvements, establishing Memory Decoder as an efficient, versatile solution for specializing large language models. Thank you for your attention. I'm happy to take questions in the comment section.